Okay, now we are trying to move towards calculation LMTD heat exchanger. Okay, LMTD actually very much famous for examiners. I think I have seen many GATE papers in mechanical, petroleum and chemistry or chemical also. They are using LMTD related formula because it's a very simple concept. If you do not understand, you will not get marks. Okay. So especially GATE exam, many questions are there using LMTD. LMTD plus some other mix up, but LMTD will be one part. Okay. In GATE also last few years petroleum trend also I have seen. Majority time 90% time they have used the LMTD thing. Okay, one problem using LMTD. Okay, so you should learn. Okay, so multiple transfer mechanism. So normally if you have on a single slab temperature let's say 100 degree and 200 degree and temperature heat is getting transferred solid body, life is easier. Q equals Ka minus Ka delta T by L. Okay, Q equals minus Ka del T by L. So this formula used. Convective heat transfer also you can you have used Ha delta T. Okay, so length was not there. But if you have multiple issues, like say you have convective heat transfer, here fluid is heat let's say 100 degrees centigrade, here maybe 200 degrees centigrade, and I have one layer or surface coating, maybe that H value will be different, K value will be for this material is different, maybe there is another material L value, oh sorry, K1, K2, maybe there will be air here, so their H value will be different. Okay, so many layers are there and heat is getting transferred. Let's say you have one tube. Okay, so tube one will be upper layer, maybe some fouling or extra deposition on metal or some dirt is there, so that will have some conductive heat transfer coefficient. Above that there will be convective heat transfer coefficient, then solid metal maybe copper conductive heat transfer coefficient. Okay, and inside also there will be maybe some again deposition or layer or dirt, again convective. So if you have to calculate this one, then single formula K equals del T by L will not work. So you have to make some combine or combination formula. Okay, so that formula is like this: Q equals UA delta T. Okay, simplified formula. So what is U, what is A, what is delta T? U actually universal constant. Universal, how they are making? Universal not like gravitational constant or like this. They are making using this K, H, some other parameters also. Okay, so this is called universal constant or overall heat transfer coefficient. Overall HT coefficient. Overall HT coefficient COE. Okay, so this unit is BTU, British thermal unit, HR FT square degree F. This is not minus, just dash dash I have given. Okay, and Q value is BTU per hour. Okay, because U is having hour term, so that's why hour is coming. If you want to convert to second or minute, then you have to convert 1. Okay, and del T temperature difference. Okay, A area. Okay, now from here this del T also not simple del T, inlet temperature, outlet temperature. Let's say if I have two pipes, okay, wait, okay, wait, not looking good, just let me draw properly. Okay, let's say one inner pipe and one another outer pipe. Okay, one pipe this one, another pipe is here. Okay. So, one pipe flow direction, let us say Q1, another pipe flow Q2, maybe same direction, both fluid flowing, inner temperature may be T1, outer temperature may be T2, two fluid, inner may be gas, out may be water, okay, and inner temperature may be say 100, outer temperature may be 200. So, 200 to 100 heat will be transferred, or opposite way I can make outer 200, inner may be outer may be 100, inner may be 200. So, heat will be getting transferred from one pipe to another pipe, one, right. So, how to calculate this in this case? Okay, it is not simple easy case. For example, what happens, this inlet temperature T inlet for outer one may be 30 degree, 30 degree to 100 degree increased, and inner one, this is 300 degree. Okay. So, inner pipe has 300 degree temperature, when it is exiting it is being 200, outer pipe inlet temperature 30 degree, exiting 100 degree. Okay. So, temperature changing for both fluid, because heat is getting transferred. So, both fluid temperature is changing. So, in that case what will be your del T? This is very difficult. So, in that case you have to use logarithmic mean temperature difference. Okay. So, how to do it? So, let us say this is pipe length. Okay. So, inlet T, outer pipe Ti increasing 30 to 100. Okay, 30 to 100, and inner pipe 300 to 200. This will not be straight, rather it will be parabolic type, 300 to 200, right. So, temperature inner pipe initially it was 300, it became 200 reduced, outer pipe it was 30, it is becoming 100. Okay. But if I have opposite case where opposite case, let us say inner pipe flow same direction, same temperature inlet 300 degrees centigrade, okay, and 200 degrees 200 degrees centigrade, but fluid direction this, okay, but outer fluid direction opposite. Okay. So, outer fluid direction opposite. So, in that case inlet temperature can be, let us say same temperature if I keep 30 degree, and outer maybe 50 degree. Possible. So, outer increased temperature 30 to 50, inner reduced temperature 300 to 200. So, how this figure will look like? So, first let us draw inner one. Inner one means 300 to 200. So, 300 to 200. Okay, and outer one 30 to 50. So, 30 to 50, but direction opposite. So, my arrow direction should be opposite, 30 . Okay. Now, because del T you have to find, del T actually LMTD, logarithmic mean temperature difference. So, LMTD when you are calculating, so left side del T1 equals, you have to say T1, this temperature difference left side T1 maybe, this is del T2. So, does not matter which side you are writing del T1 side you can write del T2 also, there is no issue, but one side del T1, another side del T2. So, here also del T1 del T2, okay, does not matter whether you are writing left side del T1, right side del T2, okay, but formula is most important. So, logarithmic mean temperature difference equals del T1 minus del T2 logarithmic natural log, not base 10, this log base E, del T1 by del T2. This is actually del t whatever you are giving in the equation 1. Okay. Equation 1 you have written del t, so that del t actually. So LMTD equals del t1 minus del t2 divided by logarithmic del t1 divided by del t2. So if you are writing del t2 minus del t1, log also will change. So the symbol will be positive finally. Okay. So you should not mix up. You are writing del t1 first, then logarithm also up del t1, then del t2. Okay. So then symbol will be positive. If you are doing some mistake anywhere, then it will be becoming negative. Negative means you have done something wrong. Okay. So this is universal formula for both cases. So only you have to remember del t1, del t2 how to write. Okay. Then after that the formula is only one formula, LMTD. LMTD is formula 1 for both parallel flow or counter flow. This is called this is same directions with parallel flow. Okay, and this is counter flow. Parallel flow sometimes we write co-current flow also. Okay, so for this one this figure, and for this one this figure. Okay. So phase change also possible. Let's say water you are taking 0 degree, high temperature, the hot fluid temperature 200 to 100 reducing, but water temperature is fixed. That is also possible, because as far as temperature difference you are creating, this formula is unique. Okay, LMTD this formula, and based on this formula I think mechanical, chemical I already told, petroleum they are using lots of problem tweaking here and there. Okay, so you should be having good command over this one, whatever I believe. Okay, so let's see some simple problem. A hot fluid enters concentric pipe heat exchanger at temperature 300 degree Fahrenheit. Hot fluid 300 degree Fahrenheit entering, it is to be cooled to 200 degree Fahrenheit by cold fluid entering at 100 degree Fahrenheit and heated to 150 degree. Calculate LMTD for counter current and co-current. Co-current means parallel flow. Okay. So both are actually parallel, but co-current normally they say parallel. So first you have to draw the figure. Okay. Before you handle any LMTD problem, first draw the figure. So your hot fluid, co-fluid, you are saying counter current. So first you draw counter current. Okay. And one co-current also. Co-current means like this. First draw. Now you put the temperature, whatever data given. Okay, you show that arrow also. Okay, so you are saying hot fluid entering pipe heat exchanger 300 degree Fahrenheit. So 300 degree Fahrenheit. Here also 300 degree Fahrenheit. Okay, this is counter. This is co. Right. Okay, now and is to be cooled 200 degree by a cold fluid, and it is to be cooled 200 degrees. So 300 200 degree, here also 200 degree. Okay, by cold fluid entering 100 degree Fahrenheit, cold fluid entering 100 degree Fahrenheit, here also 100 degree Fahrenheit, and heated 150. Okay. Now del T1, del T2. Okay, so del T1, what is del T1? 300 minus 150, 150. Here counter current del T1, del T2, 100. Okay, for co-current del T1, 200, del T2, 50. Okay, now LMTD. LMTD for this one, yes, I will separate LMTD for this one. So del T1 minus del T2 divided by logarithm of del T1 by del T2. Okay, so del T1 what is this? 150 minus del T2 100 divided by logarithm of del T1 150 divided by del T2 100. So 50 divided by logarithm of 1.5. and LMTD for this one, same formula I have to apply, del T1 by del T2. Okay. So, del T1 how much? 200 here, del T2 50, logarithm of 200 divided by 50. So, it is coming 150 logarithm of 4. Okay. So, what is the left side value? 150. Okay. So, this is coming 123.3 degree Fahrenheit. This is coming 108.2 degree Fahrenheit. Okay. So, two different values are coming, but this is the procedure. So, in exam also similar or some twisted problem can be created and it will be given. Okay. It is clear, no? So, this sort of problem you search Google, lots of problems there in mechanical get paper also I have seen. Not only petroleum also there every year. Last few years I see 2016 onward I checked every year LMTD there almost. Okay. Overall heat transfer coefficient I told U, right. So, Q equals UA del T. So, del T already we calculated at LMTD, but not only LMTD, if some other value also given, like say already fixed temperature I will be giving, okay, use this formula, this value. So, you can take that one. Okay. If that is not given, maybe you have to calculate using LMTD or some other method, that will be instructed in your question. And what is U value, right? A means area, you know, but U value you have to calculate. So, U value, like, yeah, I have one pipe. I have one pipe. Okay. So, pipe okay. So, pipe actually it is like this. Okay. I cut this one, I have cut it 50%. So, that is why it is looking like this. Okay. I just splitted. Okay. Now, I will have inner diameter of the pipe. So, I have this one. Inner diameter maybe R, radius R I, R O. Okay. So, it will have inner maybe some convective heat transfer coefficient, outer maybe heat transfer, convective heat transfer coefficient. I can have fouling also. Fouling means extra material deposit on the surface. Okay. Because of you have calcium, water is not preferred and you are using for your boiling application. So, the salts will be deposited on the surface. So, that will be dangerous sometime it will be problematic. Sometime water or fluid will have some dirt that will be getting deposited on the surface. So, metal conductivity is very high, but your scale or the dirt or fouling, that part, that heat conductivity will not be same, it will be normally lower. Okay. When heat conductivity lower, that means heat conductivity it is reducing. Okay. Your pure copper will be very high conductivity, but when dirty is there, so conductivity will get reduced. Okay. So, you have to remove actually, or you have to make some arrangement so that that deposition will not be there. So, if it is deposition is there, then what will be your heat transfer rate that you have to calculate. So, you to calculate that one actually you have to use this U value, okay, overall heat transfer coefficient. So, you may have one layer of scale, we say scale, okay, or fouling or dirt, and you have one convective heat transfer here, because from outer fluid one layer will be created, then heat will be transferred to a solid body, then again inside one layer will be there. Okay. So, then one convective layer, one conductive layer, one conductive layer, then again conductive layer maybe, then again convective layer. Sometimes there will be some multiple layer of pipe also. One pipe can be like one solid softer material, harder material. So, pipe also will have many layers sometime. Okay. Especially in electrical conductivity system, they will have many layers. Okay. So, formula is that 1 by U equals 1 HI AI plus 1 by K by L plus 1 by HO plus RI plus RO. Okay. This is the universal heat transfer coefficient. So, HI inside film, HI inside film coefficient or heat transfer coefficient, okay, convective heat transfer coefficient. So, it will be creating thin film, okay, on the metal surface. So, that is why sometimes they say film coefficient. Okay, so, you should be familiar with the term convective heat transfer coefficient or film coefficient, all the same. Okay. Again, unit you know, BTU HR FT square degree F. Okay. So, these are not minus, this is just dash I have put. Okay. So, do not be confused like minus I button. HO outside heat transfer coefficient, okay, and KL 1 by KL, K is conductive heat transfer coefficient, L means length, okay, AI pipe inside diameter and AO outside diameter, AO. RI, RO. So, if you have many other resistance also, so you can add. Okay, these are called resistance actually. Okay, so if you have many other resistance, then you can add one by one. Process heat duty. So, using sensible latent heat, process fluid temperature changes. So, sensible heat means you can measure using temperature. So, you can sense actually it is hot, it is cold. This is sensible heat, like 0 degree to 100 degree centigrade water temperature increased. So, you can sense it, you can feel it. Okay. So, this formula is Q sensible heat equals WC T2 minus T1. I think you already know, but just you should be recapping. W means mass, it is heat capacity, temperature difference. So, this is sensible heat you are calculating. But if you have latent heat, the formula will be W lambda. So, lambda is actually your latent heat BTU per pound and mass LB per hour. So, this latent heat for value will be coming BTU per hour. Okay. So, C value if you are putting in sensible heat unit. So, W is mass flow rate in sensible heat. So, if it is having unit B mass flow rate LB per hour, so QSH also will be coming BTU per hour. Okay. And C value, C unit is BTU per LB per degree Fahrenheit. And heat duty from multiphase stream QP equals QG plus QO plus QW. QG gas heat BTU per hour, QO oil heat duty BTU per hour, because all unit must be same. Okay. Q water heat duty, water again same unit BTU per hour. Okay. If you have different unit, then you have to convert and you have to make same unit, then you can add only.